First speaker is Professor Manfred Bischoff from University of Stuttgart, and his talk is entitled Variational Methods for Consistent Singular and Scale Mass Matrices, and the paper is co-authored with Anton Kachuk. Here. So the talk will be presented by Professor Bischoff. Manfred? I will notify when there's 5 minutes left. Okay.
Okay, microphone is here, all right. Yes, just edit that author here, yeah. Okay, so we're a little bit ahead of time, so I'm starting slowly. So first of all, thank you for being here, and thanks to the organizers for the possibility to talk here about this topic, which is actually the contents of Anton Kachuk's, or mostly the contents of Anton Kachuk's PhD thesis. Introduction. So what I'm talking about is variational methods for consistent singular and scale mass matrices, and it's really something I personally have not worked a lot in the last couple of years. So it's a new field for me, and probably during my talk I'm going to say things which perhaps are disputable or even wrong, of course myself not knowing it that it's wrong. So I really understand this talk also as, well, as a contribution to a discussion, and I'm happy about every comment or remark that you might have on this topic. It's really two topics actually that, well, it's said in the title already, singular and scale mass matrices, but I'm going to explain that next. So, well, as usual, let's start my presentation with the motivation, and I'm going to talk a little bit about the state of the art. And as I said before, it's mainly two topics: state of the art of explicit analysis, mass scaling, or mass scaling in explicit analysis, and for implicit analysis, state of the art of formulating singular mass matrices. These are really two seemingly separate things, achieving different goals also. The methodological framework is based on analyzed Hamilton's principle, so it's like the scientific core of what I'm going to present, and I'm also talking about a corresponding discretization. And finally, of course, I'll try to look into the benefits and possible limitations of this approach in the context of a couple of numerical examples. So just as a motivation, look at this full car crash. It's actually a very coarse car model, so in industrial applications today, people are using binary meshes, but this is just computed on a desktop machine, so the model size is not very big. The element size, shell elements are about 5 millimeters, so it's, as I said, a coarse model. It's run with Steiner here with a time step of 1 microsecond, and the overall duration of the crash is about 100 milliseconds, and this is 12 hours, well, on one node with 4 cores. And in order to understand a little bit where all the computer time goes, we looked at the first 40 milliseconds of the crash, and we see that some 70% of the clock time, but also the CPU time, goes into element processes, and another vast amount goes into the contact algorithms. So this is where we spend a lot of time. When we think of speed up of those processes, of course, there's the possibility to, well, find better elements, so we can use cross meshes or have, for a given mesh, better accuracy or faster implementation of a given element. But this is already rather efficient in LS-DYNA. Of course, you could also think of speeding up somehow the process of detecting contact and so on. But there's another circle here, which is the overall cycles. And they, of course, depend on the time step. So there's a certain potential in increasing the critical time step, and this can be done by mass scaling. And this is routinely done in industry, perhaps not so much in pressure analysis, but more in metal forming, so in applications where the inertia is not so important. So for this, well, fast short-time dynamics, it's rather demanding to find mass scaling schemes that actually pay off. So that's one of the challenges here. Well, here's another picture of an impact. That's a little bit more of a soft impact, at least I hope for this guy here. And I'm talking about implicit time correlation. So it's a totally different thing. So I'm talking about implicit analysis. Usually we are not doing that when we are doing pressure analysis. But, well, it's also doable. Okay, and what we expect is that, well, upon the transition of the energies, so before there was some kinetic energy, now there's more potential energy in the deformation of, well, the two contacting bodies. There is a more or less smooth curve, well, force versus time or energy versus time. And, well, if you're doing analysis of such a process, reducing that to 2 dimensions, so just, for instance, sending a circular disk against a rigid wall, just 2D plane specimens, we observe oscillations. So in the forces versus time, and also you see there are some wiggles here in the expression of the energy. The really bad news about this phenomenon is that if you decrease the time step, trying to resolve the problem better at time, things are getting worse. And this comes from the fact that usually on the surface of the three-dimensional structure, or this line of the two-dimensional structure, it really has zero mass. The surface itself is 1 dimension less than the actual structure. But in the discrete setting, it does not have zero mass because there are discrete masses on the surface. They produce this problem. It doesn't go away with improved discretization in time. So as I said, there are 2 seemingly separate things, one of them being explicit dynamics, for instance, pressure analysis, but that's not the only application for explicit dynamics, of course. And we want to reduce the CPU time, we want to be more efficient. And there's a couple of strategies that you can, well, follow in order to do that, but we are going to mass scaling, or more precisely selective mass scaling. And the other story is implicit dynamics and the effect of oscillating forces, and perhaps you want to see something like this blue line, which is kind of smooth, and also there is a lot of work in the literature of achieving that. Well, for instance, index reduction of the differential algebraic system by solving some surrogate problem, or some regularization procedures, playing tricks on the time discretization, and so on. But what we are going to do is we are going to look into an alternative discretization using singular mass matrices in order to solve this problem. And in both cases, so we are working with different mass matrices. And well, in Germany, we have a saying that if you're doing 2 different things with just with 1 step, it's zwei Fliegen mit einer Klappschlag, or hitting, in English would be hitting 2 birds with 1 stone, and we'll see if we achieve that, or if we are able to be able to do that. So how does mass scaling work? So what's the idea of mass scaling? So first of all, it's very simple. If you add mass, you increase the inertia, thus you reduce the frequencies, and we know that the critical time step, well, depends on the frequency. If you reduce the frequency, well, the critical time step is larger. It's very simple. Of course, it's a brutal method, because if you just add mass everywhere, so the overall spectrum is more or less wrong, so all the frequencies are too small. So you see here, that's the relationship, the relation of the frequency of the modified system to the original frequency, plotted versus the mode number. It's just a schematic sketch here. You're reducing all those frequencies. So this is why this blunt method of mass scaling is usually just applied to a small number of selected stiff elements, because it's only the one largest frequency that drives the critical time step. So it's more intelligent to do something that's called selective mass scaling, where you're not adding just mass everywhere, but just increasing the inertia of selected modes, well, predominantly the higher modes. So you keep somehow, in a certain extent, the accuracy of the low modes, which are perhaps the important ones. Of course, this depends on the application, and reducing the frequencies of the higher modes. And thus you can retain accuracy and still gain efficiency. Well, if you do it in this type of setting, in an algebraic setting, you see that the mass matrix is obtaining off-diagonal terms, and those off-diagonal terms, of course, they produce an overhead in the computational costs, so it's a trade-off. You may have smaller time steps, but computational costs may even increase because the individual steps are more expensive, so we have to take that into account. Okay, so what's the history of this selective mask scaling business? Just mentioning a couple of landmark contributions, so I'm not going to read all that to you, but there's a couple of people who have substantially contributed. Most of all of them in a couple of papers, so you see how it started somewhere in 2004. So I'm talking about selective mask scaling here. This additional originality of mask scaling has been around since the 70s. There is a remarkable work also on solid shells and improvement on the solid elements. We're going to see that later on in Pablo Barrego's talk, the work that Mahabagani is doing right now in his group at the Polytechnic. So that's also a paper from this group. Okay, so the range of applications is, well, not only hardware, as I said, but of course the metal forming is also sometimes used for biomechanics or in models where due to some geometric detailing you have some very large frequencies in small geometric details of those models. So let's look into an example of mask scaling, just a standard 300 space element. And if you use lump mask matrices, you just have a diagonal matrix. Very nice, very easy to invert. And now if you want to do some mask scaling in order to reduce the critical time step, what you can do is you're adding something, something looks like that. It's first of all a diagonal term and then minus tensor product construction of those two vectors which look like those. And these two vectors, they represent rigid body movements of this structure. So the blue one are the horizontal displacements, the red ones are the vertical translations, and the green ones, so see if the nodes are moving like that, this is a rotation. So it's not related to rotational degrees of freedom of the element. The element only has 2 degrees of freedom, but of course there are 3 rigid body ones. Well, so these additional mask matrix that we use for mask scaling in algebraic, in this algebraic selective mask scaling looks like that. And you see the rows, they add up to 0, so there's not really mass added, so the inertia is preserved. So this is for the blue ones, the horizontal ones. This is for the red ones. And well, the green ones, the rotations, you don't want to see them. They are looking, so you get a fully packed dense matrix, but well, you end up with a method that retains inertia, both translational and rotational inertia. So the existence of course is all state of the art. Existing methods that are able to accomplish that, well, they may violate consistency, pretty much because of a lack of variational consistency or variational background. It's kind of difficult to prove convergence of those methods. There might be an undecided effect on the results, so you can really control that. There are also, at least an obvious or generalized thing, for instance, higher order fundamental elements, other fundamental types, shell elements, isogeometric fundamentals, you would have
a sound mathematical basis for that. So I'm switching again. I was thinking of Monty Python before preparing this talk. You remember that guy sitting there and saying now for something completely different. So that's what comes now. So again, I'm talking about singular mass matrices and this implicit analysis and the thing with the oscillations. Okay, and well, if we're looking into a dynamic contact problem, standard discretization leads to a differential algebraic system with index 3, which is related to the fact that we have algebraic equations here in the Karish-Kuntaka conditions, but second derivatives on the displacements here in the
what you can do do is we can somehow construct a DAE that looks like that. It's the important feature that some of the degrees of freedom here have zero mass. Okay? And it's the contact degrees of freedom. So the idea is that those degrees of freedom which are in contact have no mass. And this leads to, or can be constructed in a way that it leads to an index reduction of this differential algebraic system, well, at least for the part that is in contact. Now, how do I reduce this zero? There is this very important work of Olmut and their group, and the idea in 1D, for instance, is very simple. Think of the impact of a bar on the original obstacle. It's just a one-dimensional problem, two node elements. This one element here, well, you want to have no mass here and some mass here. So what you're going to observe is that as soon as there is an impact, the first node, it may oscillate. But we don't care, because there is no force related to the oscillations, because there is no inertia, because there's no mass. And from mesh refinement, the mistake that you're making, well, it's getting smaller and smaller. And well, can we achieve that? Well, very simply by just putting the quadrature point here in this first element. It's a very brutal idea, but well, these are mathematicians who developed that. As an engineer, they actually did that. And you can do the same thing for the two-dimensional, three-dimensional case. It's pretty much the same idea. So these are special integration techniques that produce singular element mass matrices and achieve this goal. It has a tremendous effect on the accuracy and on the oscillations in the situations that I just mentioned before. Okay, this is very efficient for bulk structure. Well, in 1D, this is also a bulk structure, right? But for thin wall structure, it's not so easy to apply, because if you think of a thin wall structure like a shell, just getting in contact like this. So we want to move the mass away from the contact surface. Well, but the contact surface is pretty much the entire domain. So where do you move the masses? So it's not so easy for thin wall structures, but for bulk structures, this is a very good solution. So there's another work by Yves Bernard and his group, and this is really what inspired us to do what I'm going to talk about in a second. And this is obtaining single mass matrices from a mixed formulation. If I say mixed formulation, I mean mixed formulation in terms of mixed chemicals principle. That's what I'm showing later on. So first of all, this is a formulation using shape functions for displacements and velocities. This is how shape functions look like. They're constructed by the standard, so it's a triangle element by the standard linear shape functions plus bubble function that's here. And well, essentially with these modified shape functions and well, this shape function, which is the one for the velocity, which is constant within the element, the construction is such that for this element there is only a central node, the one that belongs to a bubble function that has mass, and all the edge nodes, they don't have any mass. Well, by that we can achieve the goal that I have described before. So this is all, once again, this is all state of the art. This is also applicable to a thin wall structure, so in a sense, if you think of that element crashing horizontally and vertically, there is all the edge nodes that are vibrating back and forth, but because they are not on the contact surface, so you're only collocating contact. Sorry, you're collocating contact on the. It's explaining it the wrong way. You're collocating contact with the massless nodes, so the massless nodes get in contact, and the node that has the mass can freely vibrate. So you don't have the oscillations on the contact force because the contact force is zero here at the node that has the mass. Okay, so that much for state of the art. So the issues of the existing method, one of the things I said before already, is they may violate consistency. They are difficult to generalize pretty much because of there's a lack of a general framework. We've seen a couple of different things like different quadrature rules, algebraic construction of different mass matrices and so on. And well, they may affect the computational results in an undecided way. So what it would be desirable is to have a variational formulation for that, which is a framework which allows us to design consistent methods for anything more or less. Okay, so we are not there yet, of course. The approach that we're proposing here relies on multi-filtration principle, pretty much the penalized Hamilton's principle that I'm talking about next. And the independent fields are linked in the weak sense via some sort of penalty formulation. We're using shape functions and subspaces for displacement, velocities, and the momentum. And well, there are additional considerations depending on the application, whether we want to have selective mass scaling or singular mass matrices. But the framework is the same for both worlds. So these two separate worlds are kind of connected here on the method level. So this is just the problem setup. So you see all the equations here, the balance of momentum, the constitutive law, the kinematics, essential boundary conditions, initial boundary conditions, and so on. And I want to emphasize here, so up to now, as you can see from the equations, we are in a linear setting. Okay, so extending everything to nonlinearity is not so trivial. And this is the standard Hamilton principle, where well the most important point in this context is T, which is the kinetic energy, and that's the standard expression for the kinetic energy in terms of the square of the velocities, and the velocities are just computed from the time derivative of the displacement. So nothing new here, nothing special. So it's internal energy and external energy, everything for a problem that has a potential, everything is linear and nice and easy. Okay, now what we're doing is we're following the idea by Carlos Felipa on the level of spatial discretization for finite elements, namely this parameterized variational principle, and applying that to the Hamilton's principle. So on top of that kinetic energy, we are adding something which is the residuals of all those equations here, like connecting the momentum with the first derivative of the displacements, or the momentum with the velocity, or the velocity with the first derivative of the displacements, and multiplying them with parameters. And the three parameters we're just choosing somehow. And this is more or less our toolbox to design whatever variational principle we would like to have. So the penalized Hamilton's principle now looks like this. If it's T0 here instead of the original T, and if we write that in a matrix setting, well, it looks like this. So we have this functional generating matrix which we can design according to our needs, well, depending on whether we want to have mass scaling, or whether we want to have singular mass matrices, or whether we want to stress more or less one of those equations. And well, it turns out that a certain choice of constant is kind of natural, but well, this is first of all the toolbox that we have. I should also mention, as we say, this is a template for kinetic energy, that templates like that have also been presented by Carlos Felipa. This is really something that experience you make in computational mechanics. So once you find something, you find out that Carlos Felipa has done it already and didn't make a big deal of it or put it somewhere in some lecture. So it's hard to find something new actually. Okay, so for the specification for selective mass scaling, well, we're just specifying the parameters like this. We're setting C3 to 0, so we are not using this part. And C1 is chosen to be minus C2. Okay, so I'm not explaining that, I'm just throwing that at you. The corresponding three-field formulation needs discretization, so perhaps you can memorize n other shape functions for the displacements, psi for the velocities, and chi for the momentum. Well, this is the corresponding semi-discrete system of equations that we are getting. So, like in finite element technology, element system of equations, and at the end of the day, we want to have a formulation that only has, well, one set of degrees of freedom. So, well, this is the corresponding definition of those matrices that appear here. So we apply some sort of elimination or static condensation to eventually end up with something that looks like that. It's a structure that looks like that, and it's just m naught u dot dot, so times the acceleration plus k times u. I'm not using damping here, so that's also an assumption, so such that it becomes an index 1 equation. is equal to the external energy. So everything linear, no gap linear. And this is the definition of M naught. It's M plus lambda naught, and lambda naught is looking like this, and it comes from an elimination of those equations. So there's just some algebra behind that in order to get to those equations. But the idea is that we are ending up with something which looks like a standard primal method, but this mass matrix is somehow different, okay? And the way it is somehow different is in this construction, and it's consistent because it comes from a consistent variational principle, which is this generalized Hamilton principle. So that's the core methodological idea. Not just throwing away the old mass matrix and coming along with a new one without a good reason. We're constructing that on a sound mathematical basis. So that's one of the core messages here. Okay, for the singular mass matrices, we're doing the same thing, but with different parameters. Okay, so now here this is fixed to -1. Later on for the mass scaling, we want to play with C1, with these parameters C a little bit. And the same thing is happening, and we're ending up with a similar structure, but now this M, let's not call that in the node, but M star is looking like this, and has some zero entry here. In order to have a zero entry, we have to obey an orthogonality condition, and that is this part is positive definite. This orthogonality condition goes down to this equation here, the lowest one on the slide. It's just an orthogonality condition on the shape functions. So by a proper construction of the shape functions, we can construct this orthogonality, and thus we can construct singular mass matrices. So that's the idea in this context. So basic requirements of such a method are consistency, accuracy, and of course the orthogonality condition that I just mentioned. And for instance, for a 3-node 1D element, the corresponding shape functions, we are not using the standard Lagrange shape functions, but shape functions that look like this. They are looking, as I said here. The properties of those modified shape functions is that they are interpolatory only at the corner nodes, not at the central nodes. But still they perform a partition of unity, and we need at least one or two in order to be able to construct that. Otherwise, in graphical sense, there is no internal point we could move the mass. Okay, so we need at least three nodes here. So these new shape functions in combination with constant interpolations of momentum and velocity lead to a mass matrix that looks like that. So the corner masses are pretty much moved to the center of the node. And the same thing, similarly, we construct for 2D elements. So you see a tensor product structure of the corresponding shape functions for the displacement. So we're just multiplying these two guys with each other. So you know that from standard form elements. And the corresponding shape functions for velocities and momentum are also computed from a tensor product structure, but we are omitting all the terms that are mixed, so we're using only those terms. So it's 5 terms for each direction, so 10 degrees of freedom for velocities and 10 degrees of freedom for displacement, for momenta. That's why it's called Q2. It's a quadratic element, V10, P10. So that's an element I'm using in numerical examples later on. So this is how these shape functions are looking like, and at the end of the day we get a mass distribution in this element that looks like this. You see the edge nodes are massless, the corner nodes and these edge nodes and the central nodes, they have mass. And in the context of a contact formulation, I'm only collocating contact at those elements that have no mass. By that, the problem with the oscillations, well, is hopefully reduced. So for the shape functions for the velocity, we could think of, well, only taking constant ones, there's different choices, or, well, taking those which have additional columns here, taking into account also the rotation, so all the rigid body modes are consistent. So here we are adding artificial rotary inertia, here all the inertia are preserved, or we could add even more, in the hope that if we have richer shape functions or richer function spaces, we get more. Well, which of those is better is just still a matter of ongoing research. So Anna Schottler is sitting here. We'll talk about this a little bit on Friday, but also with more formulations and more applications. So let's look into numerical examples in order to find out whether this framework has the corresponding benefits or, well, suffers from the potential limitations that we might have. So the benefits for singular mass matrices is, or we expect, that they remove oscillations during impact, that they might somehow improve the energy conservation, and that it's also applicable to thin-wall structures. Potential limitations, of course, is, well, this is not really potential, we know. We need at least P equal to 2 for the displacements. It's infeasible for explicit analysis because the mass matrix is singular. Okay, so you cannot invert it, and that's a pretty obvious limitation. What could happen is that we lose too much accuracy because of the poor answered spaces, and at the end of the day, well, it's not acceptable. But this is really what's a little bit application dependent. So let me start with a numerical example. So this is just a simple beam, and we apply this velocity profile as an initial velocity, and then at a certain distance there's an obstacle. Actually, this distance is really small here because we're doing linear analysis. So there's a nearby obstacle, and I'm hitting this beam against the obstacle. And well, using a consistent mass matrix, this red one is the force response that I get using a standard Newman scheme. And using the hybrid singular mass matrix, the blue one is the response. So it's force versus time, and you see all the oscillations are gone. On the right-hand side, you see the development of energy during this whole process, and while we're losing energy, well, energy is more or less preserved for this hybrid singular mass matrix. Once again, this is stupid time integration scheme, not taking into account the contact event. Of course, you can obtain similar things, playing tricks. Are not needed. So if you're sending a shockwave through a structure, probably that's not such a good method. That's also still a matter of discussion. So that was about singular mass matrices, and now coming back to something different. Scaled mass matrices, so increasing efficiency, increasing critical time steps, well, hopefully not compromising accuracy too much. That's the second story. So the expected benefits are speed up, and the other benefit is more theoretical one of the philosophical one. We have a consistent general framework, and from that we hope that we can expect much more in terms of development. So this is of course not a benefit. I can check this with the examples. Potential limitations are we have this extra expense due to the non-diagonal mass matrix. So we have to solve a system of equations. It's no longer diagonal, so it's no longer trivial to invert the mass matrix when using lump mass. And we may have a too strong loss of accuracy. So for crash simulations, for instance, this could really kill all the benefits, override them. In order to have an estimate for speed up, I'm looking at this algorithm here, so I'm not reading the whole algorithm to you. That's the one as you find it in the Belichko's book. And there's a couple of things where when you're using selective mass scaling come in. That's also true for algebraic selective mass scaling. So first of all, you have to compute it. And well, you have to do this inversion. Well, in the first step, but this is what you're doing through the entire loop. And And this is really the tremendous cost here, expense, if this elimination is expensive, if this takes some time. And there's another thing that these two terms on the right-hand side that come, so VBCs for velocity boundary conditions that come into play, but it's really this part which is the most important one. So you have to solve some equations which you usually don't do if you do explicit analysis. And so the speed up can roughly be estimated in this manner. So it's pretty much, first of all, the ratio of the time step that you have with selective mass scaling compared to the time step that you would have with lump mass matrix. Well, times some term which depends on the time you need for a solver and the element. So you see, if you spend all the time in the solver, this is expensive. You have a bad solver, then the benefit is going to be killed. But if this is done explicitly, if this is done efficiently or massive parallel or very, very optimized, then the element assembly time is dominant, and then really the speed up is more or less proportional to the decrease in time step. And that's, of course, the perfect situation. So what you see here for this Nashville's benchmark that I've shown before is, again, the spectra, and I'm comparing here the omega, so the frequency that we get for state mass matrix in comparison to the lumped mass matrix, not to the exact one. In comparison to the lumped mass matrix, because that's what you usually do when you do explicit analysis. And so this is what you get. So you see for small frequencies, we get the same result, and for large frequencies, we have a reduction. So this reduction here, if it gets larger, if I increase this constant, that means for larger constants, we have larger time steps, so we have more efficiency, but we're losing accuracy because the spectrum is getting worse and worse. If you compare that to algebraic mass scaling, like published by Olofsson, still we're looking a little bit better here. So for the same, let's say if you take beta is equal to 0.5, that's roughly what we get, is C1 is equal to 10, it's two different parameters. So the maximum frequency is more or less the same, but the spectrum, the black one, is much better than the red one because it's closer to the reference in a wide spectrum. So that's what's to be read from this chart here. Looking at results of transient analysis, this is again a simple benchmark, it's just a beam with a sudden force here. And as a reference, we take computation with the lump mass matrix using roughly 13,000 time steps, and with a C1 of 1,000, so a rather high constant, so we are significantly increasing the critical time step. We are able to complete the same thing with 719 steps, and we get pretty much the same result. So if you use algebraic mass scaling and Olofsson's method, trying to get the same step size, you can do that. You need beta is equal to 1,000, and it's more or less the same, 1,100 or 700, I don't care. But you lose a lot more accuracy. Okay, so that's the deal here. That's it. I don't know how general this remark already is. For instance, one thing that we have to say here is that here the low order modes are dominant. So if the very left part of your spectrum is good, then you can already solve this problem. For a problem which is more complex, or the higher modes are more important. Well, it may be not so good. Okay, well, this more or less concludes my talk, so I don't know if these two guys are really, if we really got them, or if we accidentally open the window and other flies are coming in. So we're just in the course of learning that and applying that to different, well, discretizations, applications, and so on. But for singular mass matrices, we really found that these benefits are there. There's a incremental increase in this removing the oscillations. And of course, there are limitations. I mentioned them a couple of times, and really this depends on the application. And for selective mass scaling, it's pretty much the same. The benefits are really there. We have this speed up, but at what cost concerning the accuracy and the time for solving the underlying system, because the mass matrix is no longer diagonal. That really depends on the application. So also here, whether the benefits outweigh the limitations is application dependent. So as far as we could see, variational selective mass scaling outperforms algebraic mask scaling. So this Sunday in Hockenheim was clearly outperformed Hamilton, but here, well, at least Hamilton outperforms the algebraic version. And I wouldn't stop without giving some ideas of what could come next. Of course, extension to nonlinearities and stuff like that, that's quite obvious. But we want to further analyze also what's behind that penalized Hamilton's principle, look into alternative discretizations, applications, non-uniform choice of mask scaling is something I didn't touch here. So up to now, in these numerical examples, I've just applied mask scaling to all the elements, which is of course stupid. So you can be much better if you just do mask scaling for a couple of selected elements, that's obvious. And what Anton Kutschel is just doing recently is a direct assembly for sparse and mask matrices, which is very spectacular and very promising, and which is why I invite you to attend these talks on Friday by Anne Schäuble and Anton Kutschel in this session on impact and question mechanics 2. It's on Friday between 9 and 11 in Sala B2, so don't miss those talks. Right. Well, thank you for being here.
Comments, questions from the audience?
We talk about the mask scaling business, or
playing with the scale, playing with the scale for the mass matrix.
well, in 1D, I think the simplest thing that we have is quadratic prime elements for 1D elasticity, wave equation. I mean, if you're sending waves to a structure with certain frequency, probably it's not working so well because then the higher frequencies are very important. I don't know if this is a good answer, but at least in 1D we saw the application of this to 1D impact, which is really working very well for selective mask scaling. If you think of the simplest scheme, I would say just quadratic elements in any dimension, so perhaps just quadratic, what's that, the Q2 elements or quadratic hexahedra, or this quadratic one, 3-node elements in 1D, and applying exactly the scheme as I showed it. That's probably the simplest thing I could think of. I don't know if this answers the question.
Thank you. Any other questions from the floor? If not, thank you very much for the presentation and discussion.